Welcome to a session on van der Waals equation of state. In this session, we will be seeing what are the causes for deviation from ideal behavior and also derivation of van der Waals equation. So, we will be finding what are the reasons for real gas to deviate from ideal behavior, and we will be deriving a more appropriate equation, that is van der Waals equation for gases. Let us see what are the causes of deviation from ideal behavior. We have considered two approximations, that is the first one, there are lots of postulates in kinetic theory, but two postulates where we find the deviation from ideal behavior. First one is volume of the molecules is negligible in comparison with the total volume occupied by the molecules. Volume of the molecules, that is how much volume or how much space does the molecules require. Okay, that is negligible in comparison to the total volume of the gas. Now, again it is a repetition, still I am repeating it, that is when temperature is high, pressure is low, the molecules are very far apart and their volume will be very high. In that case, the volume occupied by the molecule, just for comparison sake, I am drawing a picture. This is suppose when temperature and pressure are high, this is a condition, and you can see only few molecules here and there occupying this volume. Okay. Now, when the conditions are reversed, that is I am going to take the condition when temperature is low, pressure is high. Under this condition, volume will be very low. Okay. I will represent the case. This is what it would have been in the first condition, but when temperature and pressure they have been lowered, now the gas will be occupying only this volume. This is a initial state, initial condition. Now, this is the current condition. Okay, this is occupying a very small volume and you have the same number of gas molecules occupying that region. Now, what will happen? In the other case, the molecules were far apart. Okay, so they were occupying such a big volume, and the volume occupied by the molecule, you can add this up. Suppose this comes to this much of volume. When I add up all the volumes of the molecule which they are to occupy, suppose this is the volume of the molecules. That is, if I compress all the molecules so that they become very close together and they occupy only the space required by them. Okay, you do not have any vacant spaces between. So, this is volume of the molecules. Now, since this is a very big volume, you can neglect this one. But once the volume has been reduced, this volume will not change because the molecules will require that much volume to occupy. So, from a small volume, if you have to remove that volume, you cannot neglect it. When the volume is very high, it is okay, you can neglect that small volume. So, volume of the molecule is negligible only when the temperature is high and pressure is low. Under that conditions, it is okay. Now, again there is one more factor, that is we have been considering the collision diameter. Which is already mentioned in kinetic theory itself. What is collision diameter? It is the distance of closest approach. If the volume is negligible, there should not be anything of that sort. They can directly approach. But that means that the molecule requires some space. Okay, only then the collision diameter comes into picture, and therefore collision diameter also suggests that the molecules require some space to occupy. That means this space that is required by the molecules, and this space that is known as the volume of the molecules cannot be neglected. Always, under all conditions of temperature, pressure, it is impossible. Okay, so that explains one deviation, that is neglecting the volume of the molecules. Okay. Their next one is there is no interactive forces of attraction between the gas molecules. That is also cannot be true in the case of all real gases, because you can see that you can liquefy a gas. For example, you have come across that is you get solid carbon dioxide, which is also known as dry ice, and you can have many of the gases, even the cooking gas you have it in the liquid form. So, gas can be converted into liquid and gas means, that is what they do is they lower the temperature and apply high pressure and a gas gets liquefied. What does it mean? If the gas has to get converted into liquid, in gases they are very far apart, they do not have intermolecular force of attraction, maybe that is the case. But when temperature is lowered, the kinetic energy decreases, they come closer. Okay. Again I am going to apply high pressure, again the molecules are coming closer, and since they have got the intermolecular forces of attraction, they attract each other and they are held together in the liquid state. Further, if you keep on reducing the temperature and increasing the pressure, finally they get converted even to the solid state. So, this shows that is liquefaction of gases suggests that there exists intermolecular forces of attraction. So, that is one point, that is liquefying the gases. If there is no intermolecular force of attraction, you can compress them to a certain volume, still that will be a gas remaining in a very small volume. Since they have got intermolecular force of attraction, when we compress them to a certain extent, the attractive forces bind these molecules together. They are not free to move. They get converted into liquid state, and further if you continue that, you can have the gas converted into liquid state and finally to the solid state. And this is a very good example to show that there exists intermolecular force of attraction. But again, if the temperature is high and pressure is low, that is when gas molecules are far apart, you may consider that is there is no intermolecular force of attraction. Okay, that is one point. Another point, again, these molecules, that is they have two molecules, they coming together. Okay, they collide with each other. Okay, and we have a factor known as collision diameter. This collision diameter means that is the distance between the two centers of two molecules at their closest approach. Now, how do these molecules approach each other? Because they are having some attractive forces that brings them together. So, this closest approach the distance between the two centers, we call that to be a collision diameter, which proves that there exist an attractive forces, and when the molecules are brought further closer, they get repelled from each other. So, there exists intermolecular force of attraction. That is again a proof that molecules, they have intermolecular force of attraction. When they are very far, there might be not exerting any forces, either attractive or repulsive forces, but when they come closer together, the intermolecular force of attraction operates. And this is when the temperature is low and pressure is high. Now, based on this, we are going to derive another relation, a modification of ideal gas equation, rather than you can call it like that, so that the ideal gas equation is made applicable to the real gases. So, the two things we have here is these two factors, that is volume of the molecules is negligible in comparison to the total volume occupied. For there should be a correction for that, that is one point. Second one is there exists no interactive forces between the molecules, but that is again not true. So, there should be a correction for that too. So, we are having two correction terms, that is first one is the volume correction. So, we are going to derive van der Waals equation, in which we have the volume correction as well as a correction for intermolecular force of attraction. Rather, you can call that it will be a pressure correction, which we will be seeing in detail later. So, the first one is the volume correction. Just to show that this is at low pressure, the molecules are occupying a very large area. Now, pressure is increased, the volume of the molecules, they become very less. So, you can see that molecules are coming closer, and there is a particular volume which molecules require. So, that volume you will have to exclude it, because according to gas law, PV is equal to RT for 1 mole. Okay. This PV is equal to RT, in that we consider P as the pressure, V as the volume, and T as the temperature, and R is of course the universal gas constant. Now, here what does this volume mean? This volume is known as a volume where the molecules can move freely. Okay, that is free volume, or you can say that the gases have no hindrance. Suppose I am taking a gas in a 1 liter vessel. Okay. There will be some volume required by the molecules. Okay. Suppose the total volume required by the molecules, as I have shown here, suppose this is the volume required by the molecules. The volume available for the free movement of gases will be, if I take a molecule of gas, this will be free to move in a 1 liter vessel, excluding the volume occupied by the molecules. Or suppose I can draw it in another way. See, this is again a 1 liter vessel, and this molecule, I am going to consider this molecule and some other molecules in that. Not much, just to clarify that. So, this is the molecule I am going to consider. This molecule can move freely in all space except these volumes, that is the volume occupied by these molecules. You will have the free space only that much, because it cannot move in this region where this molecule is occupying, in a similar way with the other molecules. So, we require, suppose the volume as a vessel is 1 liter, it does not mean that the gas can move freely the whole volume of 1 liter, but excluding a certain volume, which is volume occupied by the molecule, or you can say volume of the molecules. That is, molecules require some volume. That volume has to be excluded, and the rest of the volume is available for the free movement of the gas molecules. Now again, see, this is, I have mentioning, this is the collision diameter. See, when a molecule approaches here, this is the closest approach, and further this molecule cannot pass through this area should be excluded. So, it is again showing that the molecule requires some space to occupy. So, again, excluding volume of the molecules, you can have the rest of the space for the movement of the molecules. So, the exact volume or the corrected volume or you can say that the ideal volume actually will be the volume of the vessel minus a factor which is responsible for volume of the molecules. Okay. And this is considered or denoted by the letter B, which is known as, it is also known as van der Waals constant, it is also known as co-volume or excluded volume. So, if I measure the volume of any gas V as V, it should be subtracted from a certain amount, and those volume, that is the value of the volume which is actually available for the molecules to move about, or you can say that the corrected volume or the ideal volume will be V minus a factor, and that factor is denoted by the letter small b, and therefore, we can represent it as V is equal to V minus B. V ideal should be equal to V minus B. Okay. So, this is the volume, or it is also known as co-volume or excluded volume, and this is a factor which represents the volume occupied by the molecules, okay, of the total volume. Next, we have to go for the pressure correction. Now, let us consider the pressure of a gas. Now, before that, what is pressure? Pressure is force per unit area, or it is in the case of gases, according to kinetic theory of gases, it is, that is, molecules, they move about in the container in a rapid haphazard motions. They collide with each other and also with the walls of the container. The collision on the walls of the container, they exert a pressure, and this is exert a force, and this force per unit area is taken as the pressure of the gas. So, collision on the walls of the container represents, if you take on all the faces of a vessel, we have the measure of pressure of a gas. Now, let us consider a molecule well inside the vessel. Okay. This molecule is surrounded by number of molecules around it, and all these molecules will be attracting, and as a result you can see that this force and this force, diametrically opposite two forces, they get cancelled. Do not think it is in a circular fashion, it is in a sphere. You can have the molecules all over here, the 3-dimensionally, and any two attractive forces which are diametrically opposite, they get cancelled. And finally, there is no net force experienced by the molecule which is within the center of the gas container. Now, suppose you can see a molecule which is near the boundary of the vessel. See, at the walls of the vessel, you can see that here you do not have any molecules, on the other side we have all the molecules arranged here only on one side. The other side you do not have any molecules and these molecules are attracting it, and finally it will have an resultant force in this direction, attractive force. Okay. So, it is having unbalanced forces near the walls. Molecule experiences an unbalanced force. Now, what will happen to that? What is the consequence of that? Now, we know that pressure of a gas, it is the force with which the molecule strikes on the walls of the container. Okay. Now, since this molecule is experience an unbalanced force which attracts the molecule backwards, just dragging it or pulling it backward. Okay. So, the force with which this will be hitting on the surface of the container will be lesser if there were no attractive forces. If there were no attractive forces, it will come and strike on the vessel with a different or a higher force. But once there are molecules which pull the molecule backward, as a result the force with which it will be striking on the walls of the container will be less. Or you can say that, and that is a measure of the pressure. So, the pressure what we measure from a gas is not an ideal pressure, that is ideal pressure is actually greater than the pressure measured. What is the reason? Just because the molecules they have attractive forces. Okay. So, it experiences an inward pull and the molecule will not be able to strike on the wall with high force. Okay. Now, what happens here is when we measure a pressure of the gas, suppose I am measuring it as 1 atmosphere, that is not the actual value. It should have been shown a higher value than 1 atmosphere, provided there is no intermolecular forces of attraction. So, the ideal pressure, if we have to get it, we will have to add the measured pressure plus one factor. I will consider that to be small p. This is a correction term for P, and this accounts for the intermolecular forces of attraction. Forces of attraction. Okay. So, this correction term for pressure is because the molecules they experience an intermolecular force of attraction. Now, how is this so? Now, this pressure correction for pressure will be proportional to number of molecules within the gas, or I put it as rho, where rho is the number density. Number density means actually density is mass by volume. Density means is mass by volume, but number density is number of molecules by volume, that is number density. Okay. So, number density rho. So, how many molecules they strike on the wall depends upon the number density. Okay. Now, what will be the retardant force? How much it will be retarding? Again, that too depends upon the number of molecules. So, twice it is proportional. That is, first case, how many molecules strike on the wall? Actually, that depends on number of molecules within the gas. If it is high, you will have a larger number of molecules striking on it. Now, the retarding force, that is the inward pull experienced, that too depends upon the number of molecules or number density, or in short I can put this, combining these two, I can put that the pressure correction term is proportional to rho square, Greek alphabet rho square, which we have mentioned it in previous sessions as the number density. Now, if I am taking the case of 1 mole of a gas, this number density is proportional to 1 by V, number 1 mole divided by V is the volume. So, I can replace P proportional to 1 by V square. Now, again removing the proportionality constant, I can put this as P is equal to a proportionality constant divided by V square. This is the case where this is what we will have to add up to get the ideal pressure. To get ideal pressure, we have to add the measured pressure plus A by V square. Okay. So, this is a pressure correction, and volume correction, we know that we have a volume from which the volume of the molecules has to be excluded. Now, what I am going to do is I am going to modify the ideal gas equation. Ideal gas equation for 1 mole is PV is equal to RT. Okay. PV is equal to RT is for 1 mole. For instead of P, I will have to take it as, actually we will be measuring the pressure P, and to that I have to make a correction A by V square. Next is into V, and for V what the correction is? V minus B is equal to RT. So, the measured pressure plus A by V square into V minus B is equal to RT. Now, this will be the ideal pressure and this will be the ideal volume, okay, in the case of a real gas. Now, this is known as van der Waals equation. DER, both are small letters. Next is capital WAALS, van der Waals equation for a gas. Now, giving these corrections, van der Waals have made the equation applicable for real gases, and this is for 1 mole. Now, what will happen when I consider n moles? When I consider n moles, we know that for 1 mole volume correction was what? B. Therefore, for n moles volume correction will be n into B. So, instead of V, we will have to put it as V minus NB. Now, take the case of pressure. The case of pressure, the pressure correction term small p was proportional to the number density rho. Okay. This rho was for when we consider the number density, again p was proportional again to rho, and we got it as P proportional to rho square. And for 1 mole we considered that to be 1 by V, and for n moles what should be this thing? N by V. Okay. So, applying that, for 1 mole rho proportional to V. For n moles, rho proportional to n into 1 by V. N into 1 by V makes n by V. So, the pressure correction will be equal to, I will put the proportionality constant A, I will put it like this, it is a proportionality constant, I will put it later, n by V whole square, okay. Then P is proportional, sorry, is equal to A n square by V square. Now, I am going to write the van der Waals equation for n moles. P plus A n square by V square into V minus n B is equal to, here I have to put it as nRT, and this is the van der Waals equation for n moles of a gas. Okay. For 1 mole, the only difference is here we have A by V square. For n moles, it is A n square. Do not forget, this n will be A square by V square, and for 1 mole it was V minus B. In the case of n moles, it is V minus NB. Here it is equal to RT for 1 mole, and here it is nRT. Okay. Next, what we have to see is the units of these terms. That is, we have introduced the proportionality constant, okay, and for the pressure term we have put A. What is A and what are the units? Since it is added to the pressure term, what should be the unit of this? It should be in pressures itself. So, A into n square by V square should be equal to newtons per meter square. Okay. And the unit of A will be equal to newtons per meter square. This is volume, volume square, that is, this is meter cube whole square. What will be that? Meter A into n will be number of moles, mole square, divided by meter cube whole square is equal to newtons per meter square. This will be m to the power 6. Okay. So, this is in the denominator, it goes over there, it becomes m to the power 6. This will be coming to the denominator mole square. And finally, you will have this as mole raised to minus 2, this gets cancelled, this becomes 4 newtons meter raised to 4 mole raised to minus 2. That will be the unit for A. This is the unit of A. Okay. For B, you can see that since there is V minus B, NB, sorry, NB. Okay. What does it mean? If we have to subtract it from volume, naturally the unit of B should be that of volume itself. Okay. So, unit of, that is NB, will be having the volume, unit of volume. So, B will be equal to, this is mole into B is equal to meter cube, or B is equal to meter cube, this will go to the denominator divided by mole, or I can put it as mole raised to minus 1. These will be the units of A and B. Now, to conclude, we have been seeing the causes for deviation from ideal behavior. What was the two causes? The two causes were, First, we assume that volume of the molecules negligible when compared to volume occupied by the molecules. But we know that this is not true when we consider the temperature is low and pressure is high, because here the molecules come closer, volume will be small, and neglecting a volume, though it is small, neglecting it from a smaller volume, it is not possible. When the volume is high, it is okay. So, again that is one of the causes for deviation. Second one was for intermolecular force of attraction. Again, when the temperature is high and the pressure is low, the molecules will be far apart. In that case, there will not be any intermolecular force of attraction, but when the temperature is low and pressure is high, the molecules come closer, and as a result there will be an appreciable intermolecular forces of attraction. Okay. Next is derivation of van der Waals equation. Just brief it. You can see that we have made two corrections. One is the volume correction. The volume correction, we included that because when the molecules are occupying a very large volume, the volume of the molecules you can neglect it, or we will not consider the volume occupied by the or volume required by the molecules. But when the volume is less, we know that the molecules, they require a certain space to occupy, or there is a volume occupied by the molecule, and these volumes are not available as for another molecules to move about, because once they come there, they get collision on that, because they cannot pass through it. So, they require a volume. So, the volume of the molecules has to be considered, and for that what we do is the actual measured volume is not exactly the volume which is available for the molecules to move about. Or you can say in another words that if you compress a gas, you can compress to that level where the molecules are of their closest approach. So, the volume which is not compressible, after that you can't compress it, because that is the volume required by the molecules. Okay. So, the volume measured by us for the molecules, it is not exactly the volume available for the molecules to move about, and as a result that volume has to be subtracted, or there is a correction that has to be employed in the volume which is considered as a ideal volume, where the whole molecule can move freely, and that is we are going to subtract a factor B, which is known as the co-volume or excluded volume. So, that ideal volume will be V minus B, and B is the correction for volume of the molecules. Okay. Now, again coming to the pressure correction. Pressure, we know that it is a force with which the molecules strike on the walls of the container. Now, when there is no intermolecular forces of attraction, the molecules are free to move and they can collide with the walls of the container with their own force with which they collide it. But once there is intermolecular force of attraction, the molecules behind the molecule which is going to hit on the surface or the walls of the container, they will be attracting, and this molecule will experience an inward pull, okay, or a backward drag, so that this molecule cannot hit the walls of the container with sufficient force. That will be reduced, and therefore, the pressure what we measure is actually a lower pressure. It is not the exact pressure, that molecule would have, that gas would have been showing a greater pressure. So, we will have to add up a term to the pressure term. In the case of volume, we subtract it because that is not available, that volume is not available for the movement of molecules, and therefore, we have subtracted it. In this case, the pressure we measure is not the pressure exactly that molecule is or the gas molecules are showing, and therefore, what we do is the measured to the measured pressure, we will have to add a correction term or a pressure factor for correcting that to be an ideal pressure. Now, for that we consider that the correction term, that is number of molecules striking on the walls of the container depends upon the number density. Again, the retarding force, how much it will be experiencing the retarding force, also depends upon the number density of the molecule. So, combining these two, we can put it at the pressure correction is proportional to rho square, which is the number density. Now, when we consider 1 mole of a gas, that is number is 1 by V is proportional to 1 by V, or we can put it as P proportional to 1 by V square. Now, making it an equation introducing a proportionality constant small a, P is equal to A by V square. Now, the ideal pressure should be the measured pressure plus this correction A by V square, and for 1 mole it is P is equal to the measured pressure plus a correction term A by B square. Now, putting that into the ideal gas equation, we are making these corrections, then van der Waals equation, we get P plus A by V square into V minus B, both corrected, is equal to RT, because this is for 1 mole. Now, we are going to consider for n moles. For 1 mole the volume correction was B, for n moles that is n into B. It is very easy. In the case of pressure, we know that correction term pressure is proportional to rho square. For 1 mole it was 1 by V, it is proportional to 1 by V. For n moles it is n by V. So, making that correction, we get P proportional to n by V square instead of rho square n by V square. Now, making it as an equation, P is equal to A into n square by V square. Okay. Now, applying this, for n moles of a gas, van der Waals equation is P plus A n square by V square into V minus n B is equal to RT, that is for n moles. Now, coming to just saying that A and B, let us see what is A. A should be something that has got the dimension of the pressure, because that has to be added to pressure, surely that should also have the dimensions of pressure itself. So, it will have the same unit as pressure. So, I can put that as A n square by V square should have the unit of pressure, that is newtons per meter square, and that is in SI units. Okay. And therefore, unit of A we can find it out as A, that is A means that is the constant, n square goes for mole square, V stands for meter cube, and that square becomes m cube whole square. Okay. That makes it as m to the power 6, 3 into 2 is 6. Okay. Now, that should be equal to newtons per meter square. Now, unit of A will be equal to newtons per meter square, taking this over here and this to the denominator, you will have n m raised to minus 2 into m raised to 6 whole divided by mole square. M raised to minus 2 and 6 get cancelled and it makes it as 4. So, newtons meter raised to 4 mole inverse. So, that is the unit of A. Now, for unit of B, we know that again V minus B, this is a factor. So, it is sure that B should be having the units of volume. Again in SI units it is meter cube. So, NB I can put it as is equal to meter cube. N means number of moles, mole into B should be equal to meter cube, and then unit of B is equal to meter cube divided by mole, or I can put it as meter cube raised to mole raised to minus 1. Okay. So, finally, we have the van der Waals equation as P plus A by V square into V minus B, which is equal to RT for 1 mole of a gas, and P plus A n square by V square into V minus Nb is equal to nRT for n moles of gas. So, do not confuse it. Here n square is there, V square of course it is there, but here for n moles it is Nb, but in the case of pressure correction it is n square by V square, and it is believed that van der Waals equation both will be more applicable than ideal gas equation PV is equal to RT, because we have made certain corrections for the deviations from the kinetic theory. And that is all for today. Thank you.